Well, in this video 6 we start section 4 of the course about vector spaces and subspaces, and more in particular we'll talk about spaces associated to a matrix A. We'll talk about the column space and the null space of a matrix, and associated with the transpose we'll have two other subspaces, which are the row space and the left null space. We'll talk about the concept of rank, and we'll use all these concepts to come with a complete solution for the system AX equals B, but now when A is general. Well, we have previously defined the notion of a vector space. It's a set with two operations, addition and multiplication by a scalar. A subspace Y of a vector space X is a subset of X, in which if you do addition and multiplication by a scalar on any two vectors in this subset Y, using any scalar C in R, well, you remain in the subset. So the subset is closed under addition and vector multiplication by a scalar, and this subset with these operations and with this closedness yields a subspace. Okay, so if you take any vectors v, w in this subspace, well, any linear combination of these vectors is also in the subspace, and every subspace of a vector space must always contain at least the zero vector. So how can you create a subspace from a vector space X? Well, you can start with a subset of vectors, which we call S here, and in general the subset S will not be a subspace. But if you consider all linear combinations of the vectors in this subset S, that's a subspace of X, and it's denoted the span of S. Okay, so what you do is you isolate a few vectors from the vector space. You take all linear combinations of these vectors, which you call the span of these vectors. Well, that's a subspace of X. And this is one fundamental way to create subspaces. A lot of subspaces are directly tied to a matrix A, and this is what we'll do here and what we'll study in this section, and we'll consider that the matrices are rectangular. So you have m rows and n columns, and m and n are in general different from one another. We'll start here with the first subspace associated to a matrix A, and it's the column space. It consists of all possible linear combinations of the columns of A, and it is denoted C of A. It is a subspace of Rm. This is because A is in R m times n. Okay, so it has m rows and columns. So a column of A is in Rm. So if you take columns of A and you take linear combinations, of course you'll create vectors in Rm. Okay, so all linear combinations of the columns of A will produce a subspace of Rm. Okay, so the column space contains all possible vectors Ax with X in Rn, and Ax, well, this can be seen as a linear combination of the columns of A. Remember that. Okay, and of course X has to be in Rn because the product Ax has to be compatible. A is in Rm times n, so the number of columns of A must correspond to the number of elements in X. Okay, so remember the system of equation ax equals b, and we have seen that one interpretation of that is there a linear combination of the columns of A to produce B? Okay, ax can be written like this. Okay, it's indeed a linear combination of the columns of A. It's x1, the first element of x, times the first column, plus x2, second element, times the second column, and so on. So this question can be restated otherwise. Okay, is there a linear combination of the columns of A to produce B? Can now be restated as, is B in the column space of A? Okay, so is B in the column space of A? If the answer is yes, well, you can find a solution to the system ax equals b. Well, we have just seen that the linear system of equations ax equals b has a solution if and only if b is in the column space. Okay, so let's take an example. Ax equals b, so this is my A matrix. Okay, so obviously we work in R3 because the elements are in R3, and we can have a look at the column space. Well, the column space is the linear combinations of the columns. There are two vectors, and if you take all linear combinations of the columns of A, you generate a plane. So in our case, the plane, okay, that corresponds to the column space is the one that I've drawn over here. Okay, and it's indeed a subspace of R cube, and it goes through the origin. Okay, I've shown the two vectors over here, the first column, first vector, and the second column, second vector. So if B is in the column space, this means that B is in the plane over here. And if it is in the plane, it can be written as x1 times the first column plus x2 times the second column. Okay, so this will be x1 over here. Okay, and this will be x2 over here. So there is a solution. Well, we have exactly the same example as before, the same vectors, the same matrix A, so the same column space, and the column space is this plane that is shown over here. It's a subspace of R cube, but now our B is different in the sense that it's not in the column space, so there is no solution. It is impossible to write B as x1 times the first column plus x2 times the second column. Okay, this is not possible. Well, we know that there is no solution, but we'll see later on in the course that you can come up with a best solution. Okay, and this best solution, well, it will involve B tilde, and B tilde is the projection, okay, of B onto the column space of A. And once B has been projected, well, there is a solution. Well, of course, B tilde will be in the column space. It's projected in the column space, and there will be what is called a least square. So LS means least square solution. Okay, and this is what we'll see further on in the course. There is no exact solution because B is not in the column space, but there will be a best or least square solution obtained by projecting B in the column space. Okay, so the next subspace associated with A is the null space of A, and it consists of all solutions x of the equation ax equals 0. So if we look for all x that make ax equal to 0, okay, and x, of course, A is in R m times n. For x to be compatible in this product here, x must be in Rn, okay? So if we look for all x that makes this equation 0, ax equal to 0, well, of course, it will generate a subspace that is now a subspace of Rn, okay? And we'll denote the null space by n of A, the null space of A. So we've seen previously that is, if A is invertible, it's non-singular, and therefore it will also be square, right? If it's non-singular, then there exists no x0 such that ax0 is equal to 0. This was a property for a non-singular matrix, right? Well, the only vector that can make ax0 is equal to 0 is the 0 vector itself, but apart from that, there is no x0 that makes sure that this equation is true. So for a non-singular matrix, or a matrix that is invertible, the null space contains only the 0 vector. Remember that the 0 vector must always be in a subspace, okay? If the matrix is square but singular, there will be other vectors than just 0 in the subspace. And in this course we do a lot using elimination, and again here we'll obtain the null space of A using elimination. Well, let us look at a small example and compute the null space of this matrix. Well, we see obviously that it's singular, so well, there will be other vectors than just the origin in the null space. So we do, as we had said, an elimination procedure. Remember that the null space is finding all the x such that ax is equal to 0. We can do what we have been doing previously and bring the system in upper triangular form. We have a pivot over here. We can compute the multiplier elements for n3 divided by pivot 3. We do the operation and we obtain this system here with this equation. 0x2 is equal to 0, so x2 here is a free variable. Okay, so x2 can be anything. So we can find what is called a special solution. Okay, and a special solution is saying that the free variable is 1 and then find the corresponding value of x1. If you set x2 to 1, well, you have to set x1 to -2. So this is the special solution. And the null space is, well, is obtained by taking all multiples of this special solution. Okay, so here you have all vectors that are a solution of this equation ax is equal to 0. This would be the same thing as if you would say x2 is equal to c over here. Okay, you plug it into this equation and then x1 is equal to -2c. Okay, you see this. So we'll work with special solutions and then take linear combinations of these special solutions. Well, let us take this special matrix here, which is actually a vector. So A here is a matrix with dimension A1 times n, okay? So the null space is AX equals 0, and if you write it, well, you see immediately this is an hyperplane in Rn, okay? And the hyperplane in Rn, we remember it has dimension n-1, okay? We've seen this in the first video of this video course. This equation, you can rewrite it a little bit differently by dividing by A1. Now we assume here that A1 is different from 0, and we can write the other obvious equations that I've written here, these ones here, below, so that we kind of obtain a system that is in upper triangular form. And here you see that there are n-1 free variables, okay? So if there are n-1 free variables, we'll find n-1 special solutions. And this is what you see over here. And a special solution is simply obtained by setting one free variable to 1, okay? So here it's x2 that is set to 1, and all the other free variables are set to 0, and then we find the corresponding value of x1 over here, okay? So we can do the same thing by setting now x3 to 1 and the other variables x2 up to xn to 0 and find x1, and you obtained this special solution. And you can continue until you say, okay, xn, we'll put it to 1, all other variables x2 to xn-1 to 0, we find x1, and we have our last special solution. There are n-1 here special solutions, okay? And the null space of our original matrix, well, it's the linear combination of all these special solutions. Well, let's take a little bit more complicated example. So the idea is to compute the null space of this matrix, and we'll first bring it to the so-called row reduced echelon form. And this is something that we have been doing for square matrices when we were computing the inverses, right? So we have to use Gauss-Jordan elimination, okay? So as usual, we start with the top left. We have our pivot 1 over here. We want to create zeros over here. So we'll use the multipliers 2 and 3. It's simply the n3 divided by the pivot. If you perform these two operations, you end up with the next matrix. So here we have created a 0 over here and a 0 over there, but also a 0 over here, okay? So when we take the next pivot, we have to go further in the line, and we obtain 2 over here, okay? So that's our next pivot. We create a 0 below the pivot. The multiplier is the entry divided by the pivot, 1, and if we perform this operation, we obtain this matrix over here. Gauss-Jordan says, oh, Mr. Jordan says that you have to create zeros above the pivot, so we have to perform this operation with a multiplier 1, entry divided by pivot, so it's a 1 over here. So here we arrive at this form here with pivots 1 and 2, and we can go to the final form where we divide by the pivots. Here we have a pivot 2, so we divide the whole line by 2, and we end up with the row reduced echelon form. In MATLAB you can do this using the command rref, row reduced echelon form. Okay, simply this command here will produce this matrix over here. We see that there are two pivots, and associated with these pivots are pivot variables x1 and x3, and there are also, well, two free variables that are associated with the columns where there are no pivots. Okay, so column 2 and column 4. So the free variables will be x2 and x4. So remember, we were looking for the null space of this matrix A, so we were solving Ax is equal to 0. And we have done lots of row operations, and we arrived at this other system of equation with, we'll call this matrix R here. Rx is equal 0. But this is equivalent because we have done, well, elementary operations, and we know that this system of equation is equivalent to this system of equations. Okay, so the solutions will be exactly the same. Remember that we have a pivot over here and we have a pivot over here. So x1 and x3 are pivot variables, and x2 and x4 are free variables. Okay, so if you have free variables, you can find special solutions. And how do we obtain special solutions? Well, we set one free variable to 1 and the remaining free variables to 0, and we find x1 and x3, which are the pivot variables. If you do this and you fix x2 to 1 over here and here, okay, so we take something here, something there, and then 0. So this is x1 and this is x3, and you find the solutions. You'll see that, well, from the first equation, okay, here we have 0 times x3, so it will not play a role, and a 0 over there. From the first equation we see that x1 has to be -2, okay, and from the other equations, well, we see that for the second equation, since x4 is equal to 0, x3 has to be 0 also. So we find here a first special solution. Okay, well, you can do the same by setting x4 to 1 and imposing x2 to 0, and you'll find this second special solution. Well, the null space is all linear combinations of this special solution. So this is the null space. Okay, so this is something that you can check, okay, because you see that A times this special solution will indeed bring 0, 0 vector. So we can see here that -2 times the first column, 1, 2, 3, plus the second column, 2, 4, 6, is indeed the 0 vector. Okay, so this is the 1 here, this one corresponds to this one, and the -2 here corresponds to the -2 over here. Okay, this is equivalent to saying a first special solution is equal to 0. You can do the same thing now with the second special solution. Let's write Ax special solution 2 equal to 0. This is the special solution. So if we write this, it's a linear combination of the columns of A, so it's 2 times 1, 2, 3, plus 0 times the second column minus 2 times the third column plus once the last column is equal to 0. Okay, so if we check 2 minus 4, 2 is 0. Well, here it's a vector, so I should write it like this. 4 minus 6 minus 12 plus 8, it's a 0. So indeed this is correct. Okay, so when you do this kind of exercise, verify that A times a vector solution, a special solution, sorry, is indeed the 0 vector. By doing forward elimination or Gauss elimination, you go from the matrix A to the matrix U, which is the staircase matrix. It's the echelon matrix. Okay, and it's actually the generalization of the upper triangular matrix when you go from a square matrix to a rectangular matrix. Okay, it acts by row operations and row exchanges are allowed. Okay, and it goes on to the next column when no pivot is available in the current row. So this is an example of a 4 by 7 echelon matrix, and the pivots are given in blue here. There are 3 pivots, and we see that in this echelon matrix we create zeros only below the pivots. Well, in this 4 by 7 echelon matrix we see that there are 3 pivot variables, x1, x2 and x5, and the remaining variables are free variables, x3, x4, x6 and x7. So there are 4 special solutions. Okay, so how do we find the special solution? Well, we fix one free variable to 1 and the remaining free variables are set to 0, and we solve for the pivot variables. Okay, and this in our case here leads to 4 special solutions. So if we continue with upward elimination, okay, from the matrix U, so we do Gauss-Jordan elimination and we produce zeros above the pivots, and then finally we divide the pivots by themselves and creating ones on the pivots, we obtain what is called the row reduced echelon form. Okay, remember that's the one that we had obtained in this example, and this one will denote R. Well, again, I urge you to work in MATLAB when you do exercises. Well, first to check your results, but also to get a grip on how you should work in MATLAB and how you should work with elimination matrices. So this matrix here is the one that we had used to compute the row reduced echelon form. We had done quite a few eliminations, okay, and these eliminations are given over here. There was also at some stage we had to divide by the pivot, so this is done over here. So one way to do this and to bring A in the row reduced echelon form is to pre-multiply A with these different elimination matrices and with this, well, diagonal matrix where you divide by the pivot in element 2, 2. This will produce the row reduced echelon form, and if you use the MATLAB command RREF, row reduced echelon form, then of course you also obtain this matrix R, and this can be used to check things. Okay, the remaining code here is to compute the elimination matrix and to compute its inverse. The rank of a matrix is the number of pivots of that matrix that are non-zero, and it will be denoted R. This means that the matrix can be reduced to R non-zero rows. So if we come back to the example that we treated previously, here it is, and we ask ourselves what is the rank of the matrix A, we see here that it is 2. There are 2 non-zero pivots. Okay, this means that the matrix can be reduced, as you can see, to row reduced echelon form with 2 non-zero lines. It also means that we can find at most 2 independent rows and at most 2 independent columns. So we can talk about a rank 1 matrix, and rank 1 matrices obviously have only 1 pivot. Okay, this means that every row is the multiple of the pivot row, and we'll call the pivot row V transpose. Or you could say that every column is a multiple of the pivot column. Okay, and we'll denote this pivot column by U. Okay, this is indeed the case. This is 3 times the pivot column, and this is 10 times the pivot column. This row is 2 times the pivot row, and this row is 10 times the pivot row. And in this case, we can write the matrix as a product U V transpose. Every rank 1 matrix can be written as the product of a pivot column and a pivot row. Okay, so let's have a look at the null space. So we have to look for the solutions X such that AX is equal to 0. We rewrite A, and we see by associativity that the X such that AX is equal to 0 are X that are such that this equation is valid. Okay, this means that X is perpendicular. This can be viewed as a scalar product X, that X is perpendicular to the pivot row. Okay, so the null space, X is in the null space, is perpendicular to the row space. We'll talk about the row space later, spanned by this pivot row V transpose. We can, of course, compute the special solutions. We have here our pivot. So x1 is the pivot variable. x2 and x3 are free variables. So in this solution over here, we have fixed x2 to 1, and we find x1, and in this one we have fixed x3 to 1, and we have found x1. And the null space is a linear combination of these special solutions. Okay, and indeed we see that the pivot row is perpendicular to every special solution. Okay, so this is our matrix A that we had considered before. We had done Gauss-Jordan elimination and obtained the matrix R. Okay, and all these eliminations that you've done, or that we've done, well, you can combine them in this elimination matrix E. Okay, this can be computed in MATLAB. It's not very important here. So E times A is R. Okay, so this is the row reduced echelon form of A, and what we will see is that the column spaces of A and R are different. But before we do that, we can see that pivot columns are not combinations of earlier columns. This is true in R, but it is also true in A. For instance, this column is not a combination of previous columns. It's null because you have zeros over here, right? Whereas free columns are always combinations of earlier columns. These combinations are the special solutions. Okay, so this one here, this column, -2, 2, 0, and now I'm now working in the matrix R, is equal to minus 2 times the first column plus 2 times the third column. The first column is a pivot column and the third column is a pivot column as well. This is kind of obvious to see in the row reduced echelon form, but it's also true if you work in the matrix A. The fourth column, 2, 8, 10, is a linear combination of the previous columns. And how can you write it? Well, it's all written over here. It's minus 2 times the first column of A plus 2 times the third column of A. Okay, so these are the two pivot columns. Okay, and here there's a minus, of course, and because there is a minus over here. And indeed you have 2 is equal to minus 2 plus 4, 8 is equal to minus 4 plus 12, and 10 is minus 6 plus 16. So indeed this is correct. Okay, I return now to what I've said before. The column spaces of R and A are different. Well, the column space of R, it's alpha times the first pivot column plus beta times the second pivot column. Okay, why do I do not need to put the 3 columns in here? Well, simply because they are linear combinations of the pivot columns. Okay, so to compute the column space of R, I only need to take the pivot columns and take linear combinations. Well, to compute the column space of A, it's the same thing. I know that this one here is 2 times this one. I know that this one is minus 2 times this one plus 2 times this one. So to compute the column space, I only need to consider the pivot columns. So it will be gamma 1, 2, 3 plus delta 2, 6, 8. Okay, and we see clearly that the column space of R is different than the column space of A. This is because we have done row operations, so column spaces are not preserved. So to compute the column space, the procedure is to do elimination. You bring your matrix from A to R, to row reduced echelon form. You isolate the pivot columns, and then to compute the column space of A, you need to take the equivalent columns but into the matrix A, and this will produce your column space of the matrix A. So we would like to find a way of finding the special solutions in a systematic way, so that we can find the null space in a systematic way. So our matrix A is such that it is M times N. It has R pivots, so R is also the rank of the matrix. So if there are R pivot columns, there are N minus R free columns, so there are N minus R free variables. Okay, for every free variable there is a special solution, and the null space is the combination, the linear combination of every special solution. So we could also stack these special solutions in a matrix, and we'll call N this matrix. In N, all special solution columns are stacked one next to the other. Okay, so suppose that we have found the row reduced echelon form, and for the sake of the argument, that the first R columns are pivot columns. Okay, so these are the first R pivot columns, and the next columns are the n minus R free columns. Since the rank of the matrix is R, there are also a number of rows that are zeros. There are m rows over here. So if the rank is R, there are m minus R rows of zeros. Okay, in reality things will be a bit different because pivot and free variables are mixed, but we'll see how we can deal with that later. Okay, so we can now find the n minus R special solutions by constructing n in the following way. So we take this matrix over here, F, okay, and we put a matrix, an identity matrix of dimension n minus R below. Okay, this will be our matrix n, and you can see that if you multiply R with n by construction, what we'll obtain is a zero matrix. Well, let's test this systematic way to obtain the null space. We had a matrix R that we had obtained using Gauss-Jordan. In our theoretical approach, we had said, well, you can write R as a identity matrix of dimension, the rank of the matrix, matrix F over here is 0, 0. Okay, so here we have R columns, n minus R columns. Here we have R rows and m minus R rows, and the idea was that you could construct n as minus F with an identity matrix of dimensions n minus R. Okay, so here m is equal to 3. There are 3 rows. N is equal to 4. There are 4 columns, and the rank is 2. There are 2 pivots over here. So let's have a look if we can use this theoretical approach. Well, the first thing that you notice is that R is not in this form. Okay, here we had assumed that the R pivot columns came in front. Here they are mixed. The pivot columns and the free columns are mixed, but by interchanging these columns you end up with this form. Okay, so we can construct our n, our intermediate n, looking at F. Well, F in this case will be 2 minus 2, 0, 2. So n will be minus F with a identity matrix of dimensions n minus R, so 2. So this gives minus 2, 2, 0, minus 2, an identity matrix of dimension 2. So this is the n. But this is for a R in this form. Okay, we've seen that we have swapped the columns over here, so we need to swap the columns over here, and this leads to the final, and this was a temporary n. The final n is minus 2, 2. We swap the rows, 1, 0. Okay, 0 minus 2 and 0, 1. Okay, so the null space is, well, alpha minus 2, 1, 0, 0 plus beta times 2, 0, minus 2, 1. Okay, so here we should check that A times this vector yields the 0 vector, and that A times this vector yields the 0 vector. we can have a look at what we had found previously. Okay, and we see that indeed we have found the correct special solutions. Well, we want the complete solution to ax is equal to b. Okay, and a here is in R m times n, so there are m rows, n columns. Suppose that you have a particular solution, we'll call it xp, to the system ax is equal to b. We know how to solve the system ax is equal to 0, so we look for this null space matrix n. We've just seen how you can find it in a very systematic way, and then you obtain the solution xn by taking linear combination of these columns of n. Okay, and now we are looking for any solution x to ax is equal to b. We have already a particular solution, so by taking the difference between these two equations, you see that a times the difference x minus this particular solution is equal to 0. So this must be xn, this solution that we can find. So we see here, and this is what is written over here, that any x that is a solution to ax is equal to b can be written as x is equal to a particular solution plus the solutions of the equation ax is equal to 0. We have a systematic way of producing this one. We would now like to have a systematic way to produce the particular solution. Okay, so we want to find a complete solution to ax equals b. We have already seen that x can be written as xp plus xn. This one we know how to find it, so we are looking for a way of finding xp, right? So we start from the augmented matrix where we put a and b right next to it, and we bring a in its row reduced echelon form. Okay, so again, for the sake of the argument, we'll assume here that the first r columns are pivot columns. Okay, even if we know that in reality, well, you have to see that there are pivot and free variables that are mixed. Okay, so if we bring this augmented form into this form over here, and we assume that the first r columns are pivot columns, we obtain something like this: er f rows of zeros over here. So this is of course r, and by doing these operations to produce r, we'll transform b in a vector d, and we'll write it dr and dm minus r. Why do we write it like that? Well, because we know that there are r rows, pivot rows, and m minus r rows of zeros. Okay, so here we have r pivot columns and n minus r free columns, and this is my vector d, and in general it will be rewritten like this, right? Well, we see that in order to have a solution, this one has to be 0, otherwise we'll end up with equations of the type 0 times a variable is different from 0. Okay, so if this one is different from 0, there are no solutions. So below we'll assume that this one is equal to 0 and that d takes this form over here. Yeah, and if it takes this form over here, we have m minus r zeros over here, so we'll have a solution. It can easily be seen that we can construct a particular solution in this way. So we take the dr over here, we put it in over here in a vector, and we put n minus r zeros below. And by construction here, this equation will be valid. Okay, so now we also have a way of producing a particular solution. So now we are able to find a complete solution to ax equals b in the general case. Well, let's apply this to the system ax equals b that is given over here. We had already brought a in its, well, row reduced echelon form, so this is r. Okay, and if you would do the computations that you do to bring a over here into row reduced echelon form, and you would do the same operations on b, you would find here a d. Okay, so we see that the system is not entirely in the form that we had in the previous slide, but if you swap things over here, okay, then you see that indeed you bring it into the form ERF and 0, 0. Okay, so it's easy to obtain the matrix N. Okay, so you write minus f, in our case it will be minus 2, 2, okay, 0, minus 2, 1, 0, 0, 1. And then you swap things, okay, and this was my temporary n, and the final n is given over here. Okay, so can we now find the particular solution? Well, the particular solution was to take this thing here, which we had called dr. So xp, and it will be also a temporary particular solution, will be minus 2, 1.5, and we have r equals to 2, m equal to 3, and n equal to 4. Okay, so to be compatible we had to put a number of zeros, which was n minus r, so it's 2 over here. Okay, it's kind of logical because r times x has to be compatible, so I need 4 elements. Okay, but this does not take into account that my r was not in this form that is given over here. So what do I have to do? Well, I have to switch these rows over here, and this will produce me what I have got over here. Okay, so the complete solution is the particular solution that I have found, and I take the columns of n. Okay, these are my special solutions, and I need to take linear combinations of these special solutions. So this gives me the overall solution of the system ax equals b that is over here. Well, let's apply this to a simple example here. We have 3 equations and 4 variables, and I've already brought the system in the augmented form. So we have the matrix A over here and the vector B. We can now start with the Gauss-Jordan elimination. We start at the top left, so here is our pivot. We already have a 0 in element 2, 1, so we need to do only one operation to bring the element 3, 1 to 0. The pivot is simply the n3 divided by the pivot, so it's a 1 over here. So the next matrix is 1 3 0 2 1. We have 0 0 1 4 6, and we'll have 0 0 1 4 and 6. Okay, so we had our pivots over here. We go to the next line and we have to go up here to find the next pivot, right? So we need to produce a 0 below this new pivot, so we have to do this operation over here with multiplier 1, entry divided by pivot. Okay, and this will produce the next matrix 1 3 0 2 1, and here I can copy the second line. Okay, and we'll have zeros, 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 and zeros. Okay, so the pivots are over here. So this system has indeed a solution, because we have zeros over here, but in the equivalent elements on the other side we have zeros also. If we had had something different from 0 over here, of course we would have had no solutions, right? So remember that we are working with this. So this is my R matrix, but we have worked with an R matrix which was IR F 0 0. This was my R matrix. In our case we have R n minus R, R m minus R, so m is equal to 3, n is equal to 4, and R is equal to 2 over here. In order to obtain this matrix in this form, we have to swap these two rows. We can now obtain our temporary n. Okay, our temporary m is minus f, and we have to put an identity matrix of dimension n minus r, so it's 2 over here. So if we write that, we have minus 3 minus 2, 0 minus 4, and an identity matrix. And we can also obtain our particular solution, our temporary particular solution. What we do is take the dr over here, this one, 1 6, and we put 2 zeros below. Okay, so this is my matrix n and my particular solution if we had had our R in this form. Okay, but we had to swap columns. Okay, so what we'll have to do here is swap the columns over here and swap the columns over, not the columns, the rows. I need to swap the rows and I need to swap the rows. Okay, so my n is now minus 3 minus 2, 1 0 0 minus 4, 0 1, and my particular solution is 1 0 6 0. So my global solution is, well, you take the particular solution 1 0 6 0 plus c times minus 3 1 0 0 plus d times minus 2 0 minus 4 1. So this is my global solution. You should of course check things, okay? So if you take a times xp, you should obtain 1, 6 and 7, okay? And if you do a times a, the first particular solution, you should have 0, 0, okay? And if you do a times the second particular solution, you should have 0, 0. These are things that you could check, and at the time of the exam I expect you to do this kind of check.